Okay, good morning, good afternoon, good evening, everybody. My name is Hyunsoo from National University of Singapore. So today I'm going to talk about spin orbit talk of topological spin textures and magnons. So if you look at the recent success in spintronics community, this spin transport talk based MRAM, has been successfully commercialized in various applications. So as an academician, now we have to think about what will be the next generation magnetic memory technology. So we often talk about this spin orbit talk-based magnetization switching can be one alternatives in which we can generate spin accumulation either by bulk spin Hall effect or by the interfacial spin orbit coupling effect. The detailed mechanism is still under debate. However, the bottom line is we can accumulate enough spin current to switch the magnetization at room temperature by just applying a current along the plane direction. So if I summarize this field into three major layers, first we have to generate spin current, then we have to absorb those angular momentum. Then we can also think about the role of the capping layer, which was largely ignored. The goal is to achieve low switching current. So people try to find material systems which can give us a large effective spin or angle or a large effective spin orbit torque field. However, if we look at the total power consumption, it was found junction resistivity is also very important. So eventually, the most important parameter is a large spin conductivity rather than simple spin Hall angle. So in this talk, I'm going to mostly focus on how can we generate the large spin current using these fancy topological materials. So if you look at the prototypical 3D topological material, which is bismuth selenide, it has a peculiar spin density of state depending on the momentum direction, whether we inject the electron in one direction or the other direction. The supported spin direction is always right angle to the electron momentum direction. So we call this is a spin momentum locking phenomena. So we can, expect effective very large spin Hall angle because it looks like a spin highway depending on the electron momentum direction. The spin direction is fixed. So lots of researchers, investigated the effective spin Hall angle from these topological insulators, and the reported values are scattered, from as small as 10 to -4 up to hundreds of effective spin Hall angle. So initially, I thought what a mess, but then it was found. Thickness, play a very important role. For example, if you look at this small value, it's coming from kind of bulk sample in hundreds of micrometer, and then people use tens of nanometer. If you look at those two reports from my group, some people use several nanometer down to 3 nanometer, and you can see some kind of correlation. If somebody uses very thick films, the efficiency is low. If somebody uses thin films, efficiency increases. Of course, there are some other roles which I'm going to discuss later on. So we thought maybe it's good to study systematically in one group, various thicknesses and evaluate those effective spin or angle. So we grow bismuth selenide using molecular beam epitaxy, and then systematically studied the thickness dependence. As you can see, as we make it thin, the effective spin angle increase from 0.3 up to 1.6 using 5 quintuple layer. And this can be explained by a very interesting contribution from different bands. For example, we always have a bulk band. If the film is thick, then Also, we have two-dimensional electron gas. And the most important thing is this topological surface state, which we want it to be dominated. But in the bulk, actually, is dominated by the bulk state as well as the other two. As we make it thin and thin, now the bulk contribution is getting smaller and the other contribution is getting larger. And eventually, once we make it very thin, we can have dominated transport by the surface state and some contribution from the two-dimensional electron gas. So because of this region, we can have very large effective spinor angle if the film is quite thin. This is in a big contrast to the conventional bulk spinor materials like platinum. In this case, we have to increase the film thickness, then initially it increase and saturate, showing a conventional bulk spin Hall effect. So you can see, in bismuth selenide case, it has opposite thickness trend, and we can attribute this is due to the surface dominant effect. So we choose 8 nanometer, about which is a quintuple layer, as our spin current generation layer, because it gives a relatively large effective spinor angle, but always we have to think about the total device resistance, which can generate also less power consumption. So by having this 8 nanometer bismuth selenide, we can deposit nickel ion on top. Then we chop down this nickel ion into many different squares with a different coercivity and anisotropy. Then this is more microscopic image from the top view. We can inject the current, charge current from left electrode, and all the black color indicate the magnetic domains are saturated in this direction initially. Then we can see white domain, spread, and eventually all the magnetic domain, pointing opposite direction. Then we can apply charge current from right electrode, and then we can go back to the initial magnetic configuration. The current switching current density is about 6 times 10 to 5 ampere per square centimeter, which is like 1 to 2 orders smaller than conventional heavy metal, without magnetic field because we are dealing with the in-plane magnet. And we were able to deduce a quite giant effective spinor angle of 1.75 in this case. So you can see, this kind of fancy topological materials can be utilized as current source at room temperature to switch 3D ferromagnet. And we try to find, there must be some other role of the scattered effective spinor angle values. Then we also got to know temperature, also plays an important role because different group, reported the value at different temperatures. And as we cool down, the sample, we found the effective spinor angle maintain kind of similar value down to 100 Kelvin, but below 100 Kelvin, some device, show a giant, very abrupt increasement of this effective spinor angle. This is the intrinsic nature, coming from the surface dominant effect, because those surface band structure is triggered, below typically 100 Kelvin. The other region we found is due to the interface effect. So we fabricate 2 different devices, one using the conventional ex situ method. In this case, we grow bismuth selenide in MBE chamber, then we take it out and immediately put in the sputter chamber to grow ferromagnetic layer. In this case, we find the temperature enhancement at lower temperature is moderate. However, once we use the same MBE chamber to grow ferromagnet, so everything is done in one MBE chamber. So we call this is in situ method. In this case, we find a very abrupt enhancement below 100 Kelvin, and then effective spinor angle can even reach around 5 at 20 Kelvin. So in order to find out what's going on at the interface, we try the TEM, and then we can see the interface layer in which we can see atomic intermixing and diffusion, increases in ex situ cases, much thicker interfacial layer compared to in situ case. And from those, we can deduce the spin diffusion length is 1.755 times longer in case of in situ. So basically, spin current can easily go through this interface and affect, spin torque in this ion layer. By looking the EDX line scan, we can see there is a huge enhancement of cellular peak at this interfacial layer in case of ex situ case, which shows also, promoted atomic intermixing and diffusion of cellular if we utilize a conventional ex situ case. So finally, we were able to identify, 3 roles. The first one is thickness dependence, right? So once we use thinner films, basically effective spinor angle will increase. The other one is temperature effect. Once we cool down, basically we expect effective, large spinor angle due to the more involvement of surface band. The other enhancement, could be attributed to the interfacial treatment. So different group use basically, different interfacial treatment and their recipe. So which can also affect the scattered effective spinor angle values. So far, most of the group utilized molecular beam epitaxy to grow bismuth selenide and other topological insulator materials. However, that is not compatible with the industrial commercial process. So some group tried to grow this bismuth selenide using sputtering. For example, Minnesota reported very large spinor angle of 18.6 and a very low critical switching current density. So we also tried to grow bismuth selenide using sputtering, and then we found also very large spinor angle up to 45 for 10 nanometer films. And in our case, the switching current also, very low switching current density. However, once we calculate the total power consumption, there is no advantage because our film turned out to be about 100 times more resistive compared to our MBE films. So the question is, what is the role of surface state in case of this sputter-based growth, because the film is not crystalline, and whether the surface, state, it even exists. I think that is some outstanding question, to be resolved in the future. But anyhow, we find in terms of the total power consumption, there is not much advantage using these topological insulator materials. As the name stands for, it's basically insulator. So if you put 3D ferromagnet, basically you will have a huge current shunting effect. We try to utilize another kinds of material called Weyl semimetal. This is a cousin material to topological insulator. However, it has a conducting bulk state and as well as a very strong spin-orbit coupling in the bulk. So we do not need to worry about, this current shunting effect through the bulk. So we basically, fabricated a similar device structure based on tungsten ditelluride, which is one of the prototypical Weyl semimetal. Then we deposit permalloy on top. Then we can pattern the device and apply current from one of the electrodes. Then initial black domain can be switched to white, and white domain can be switched to basically the initial, black at the current density 3 times 10 to 5 ampere per square centimeter, which is a few times smaller than the case of topological insulator. Once we studied the thickness dependence, we found effective spinor angle increase as we increase the tungsten ditelluride thickness, which indicate we have significant bulk effect, like a platinum-like effect. And because this material has relatively low resistivity, we found the total power consumption is about 20 times smaller compared to that of bismuth selenide. Now we can try to combine this interesting material with the concept of geometrical domain well pinning device. So we propose, once we have this dumbbell-like shape and then nucleate domain well, then we can just push this domain wall back and forth between this neck point with low switching current, and then we find there is about 2 to 3 times reduction in switching current because we don't need to nucleate domain wall in every switching. And this scheme is also easily integratable with the conventional MTJ structure. So we adopt this dumbbell pattern switching device. Then we utilize the Molly, MOTE2, which is a cousin material of WTE2, then deposit permalloy on top. Once we adjust the current intensity, domain wall will always pin at this neck point, and because the current density in this rounded part is smaller than the channel. So we can move this domain wall from one neck to the other neck and back and forth with relatively low current density. And we found due to the domain wall doesn't need to be nucleated in every switching moment. We found about 3 times reduction of the switching current density and about 10 times total switching power compared to a conventional rectangular channel. So finally, we find using these wire semimetals, we can have an advantage of much smaller power consumption compared to topological insulator cases. So far, my discussion is based on exfoliation of wire semimetals, which is also a disadvantage in terms of commercial effort. In order to apply some real applications, we need to utilize wafer-scale films. So we have this CBD grown tungsten ditelluride thin films, which is quite uniform. Then first we use terahertz emission measurement to see their spin direction. Once we shine circular polarized light, we can couple either up or down spin, and then just measure, the emitted terahertz. We can deduce what is the spin photocurrent in this device. So by just changing the helicity of the excitation laser, we find sometimes positive or negative spin photocurrent that is connected with the either up spin is moving one direction or down spin current moving opposite direction. So we were able to identify basically outer plane spin texture at room temperature at this material when we apply, when we have the photocurrent along the A direction, because this material is very anisotropic, and when we apply or flow the current only the A direction, will have a symmetry breaking, so which can generate outer plane spin texture. We can also utilize conventional spin torque ferromagnetic resonance measurement, STFMR, to look at outer plane spin texture. In a conventional platinum nickel ion sample as a control, you can see the symmetric and the anti-symmetric component has basically mirror symmetry across this magnetic field. However, if you look at the tungsten ditelluride with permalloy, the anti-symmetric component, which is shown in this color, you can see is very different. So from some of the well-developed analysis, we can find what is the in-plane spin conductivity and out-of-plane spin conductivity. And then we can also convert them to effective spinor angle of in-plane 0.13 and out-of-plane spinor angle about 0.03. So we can identify this material can generate not only in-plane spin, but also out-of-plane spin, which could be very useful for the field-free PMA switching devices. So we keep continuing our conventional MOC microscopy-based switching using permalloy on top of only 5 nanometer tungsten ditelluride in this case. And then depending on the charge current direction, we can switch from one to opposite, and then we can bring it back to the initial domain at a relatively low switching current density. And This is quite meaningful because we now use the much thinner tungsten ditelluride compared to previous exfoliation case. So if you look at the conventional exfoliation case, we had to use tens of nanometer to see reasonable spin Hall effect. But here we were able to see only with the 5 nanometer sample. I think this is the first demonstration of large-scale 2D spin source-based SOT switching. So finally, I want to move to the other topic. So even though we were able to enhance the total power consumption and also see the switching using CBD-based films, still the device resistivity is, much higher, about 1 order higher to 3D ferromagnet. So we will have a huge current shunting because these topological materials, in general, they are quite resistive compared to our 3D ferromagnet, which we typically use in our industry MTJs. So one way to mitigate this is to put a insulating anti-ferromagnetic material. Then this material is basically insulator, so there will be no charge current injected. So all the current in this spin source layer will just go through this layer without shunting. Then the question is, how can we switch this free layer in MTJ? That can be achieved if this insulating anti-ferromagnet can support magnon transport. And the spin current generated in this spin source layer can trigger magnons, and magnons can propagate in this anti-ferromagnet, and then it can switch this magnetic layer. So that's the scenario how we can switch using the magnon torque. The main question is whether the magnon intensity is strong enough to switch 3D ferromagnet at room temperature. If we can achieve those, I think one of the advantage is we can relax modern complex interconnect issues. If you look at the modern memory or any logic device, we have very complex interconnects of tens of layers. And basically that is achieved by having holes called the via, and we have to have a physical contact between the current injection layer into the magnetic elements. But if we can do this, we can put an insulator material in between current flowing layer and the magnetic or memory object. So we can basically isolate those two components. So first we study using spin to ferromagnetic resonance measurement. So we inject the nickel oxide in between bismuth selenide and nickel ion, and then study as a function of the nickel oxide thickness. Then we find the STFMR data. Initially, effective spinor angle decrease quickly as we increase the nickel oxide into a few nanometer. Then, very interestingly, above 10 nanometer, we start to see enhancement of this effective spinor angle, and it has a peak around 25 nanometer. And then further increased nickel oxide thickness, effective spinor angle decreases. It has a very weird behavior. To make sure this is real data, we use opposite process. In this case, we excite our layer with the femtosecond laser, which will generate spin current in magnetic layer due to the spin imbalance. And then it diffuses with a different velocity as we cool down. And that will trigger the magnons here. And that magnon will be converted to charge current in this bismuth selenide layer due to inverse spin-orbit effect, which will generate the terahertz. So we measure the intensity of terahertz as a function of nickel oxide thickness. And once we summarize those data, you can see this open circle shows the terahertz intensity, which matches quite well with that of STFMR. So we can confirm near Fermi level, low energy excitation. In this case, we inject charge current and convert it to spin current. And at the same time, we use a very large energy, 1.55 electron volt laser excitation. So this is like a hot electron, injection. Some people call super diffusive current. Then this is the conversion from spin current into charge current. So this is an inverse effect. So we use a kind of forward and backward measurement, and both quite well agree with each other about the efficiency. So we can believe this thickness trend. And the other way to make sure this is magnon related is measuring temperature dependence. The magnon behavior will be maximized near blocking temperature, because spin can fluctuate around the blocking temperature easily. So if you choose a different thickness, for example around 25 nanometer, the nickel oxide will have about the 200 Kelvin blocking temperature. So the spin efficiency should be maximized around 200 Kelvin in case of 20 nanometer, 25 nanometer nickel oxide. So anyhow, we choose 25 nanometer nickel oxide because we believe this, shows a real magnon transport. Then is insulating enough to prevent any charge current, shunting. So we use this 25 nanometer nickel oxide in the middle of bismuth selenide and nickel oxide. Then we inject charge current underneath bismuth selenide, and then initially this isolated magnetic dot of nickel ion is pointing one direction, but after certain current density, we can see it switch to opposite direction, and by applying charge current from opposite electrode, and we can see we were able to switch back to the initial configuration. So once we look at the thickness trend, initially we have a sudden quenching of this effective spinor angle, which is not related to magnon. I think this is related to spin mixing conductance. But once we look at the thickness trend above 25 nanometer, by feeding those data, we can find out the magnon decay length is about 30 nanometer. So we try to look at the details in a thinner regime in terms of thickness trend. So we use also platinum as a spin current generation layer, and then study nickel oxide as a function of those thickness, and then put cobalt on top, and then measure terahertz emission. And then we see a small enhancement around 0.5 nanometer of nickel oxide. Then after that, we have monotonic decay. This thickness trend is similar to previous reports in which they use platinum nickel oxide YIG using spin pumping. They see some enhancement at around 1 nanometer nickel oxide. Another group reported using spin ZBAC, and also they find the enhancement around 1 nanometer, and after that there is a monotonic decay. So the peak is at 1 nanometer, or in our case 0.5 nanometer, we believe that is the basically modulation of spin mixing conductance. It's not the magnon transport evidence. The reason why I'm talking this is because the band gap of nickel oxide is a function of thickness. If we have only 1, 2 monolayer, basically we can see quite large density of state in the middle of the band gap. So this material is not an insulating material, it's a partially conducting. So we need to increase the nickel oxide thickness to develop a full band gap structure so it can work as a real insulator. So once we put like 1 nanometer, basically this is some kind of a modulation layer between two very different materials. And once you insert, you can enhance basically spin mixing conductance. So we try to look at what is the speed of this magnon transport in nickel oxide. So by just changing the nickel oxide thickness and then measure the emitted terahertz time in time domain, then we can find out basically the velocity of magnon inside nickel oxide. So by measuring the delay time and divide by the nickel oxide thickness, we can deduce the velocity initially increase up to around 20 nanometer of nickel oxide, and it can reach, like 600 kilometer per second. This is about 1 order larger than previous estimation of 40 kilometer per second using dispersion relationship. At that time, there was no time domain measurement. So it looks like in a nanoscale, we can see much improved magnon velocity compared to previous inelastic neutral scattering based measurement. So as a quick summary, I showed you mostly spin-orbit technology-based magnetization switching. Initially, we used topological insulators. Then we found there is a dominant surface transport with very large resistivity, which is a disadvantage in terms of the total power consumption. So then we utilized the Weyl semimetals, which has surface as well as bulk transport. Due to much smaller resistivity, we were able to see much smaller power consumption compared to topological insulators. But in order to eliminate the current shunting completely, we propose a magnon torque could be one direction. But however, in this case, still there is a loss penalty using magnon torque. If you look at zero nickel oxide thickness versus the peak due to the magnon, the efficiency is about half of the zero thickness case. So we still need to think about how to improve this efficiency using magnon, so we can have no penalty using magnon torque. So for this, I want to thank many of my group members and the previous group members, as well as the collaborators. Okay, thank you very much.